Hi guys. Okay, here we are, chapter 21. This is going to be our last chapter for the year. Yay, great rejoicing. And it is going to cover acids and bases, and then we'll talk a little bit about salts in there. These, as you probably know from like the little intro that you guys have already done, are substances that you're pretty familiar with, just as far as using them or eating them or whatever it is. Probably there's a little bit for you to learn as far as chemically. So first of all, taste, which we've already talked about, but just to remind you, acids have a sour or kind of a tart taste to them. Many fruits contain different acids, and so they give a very specific taste, and depending on the ripeness of the fruit, the acid may be more or less concentrated, which could contribute to the tartness or the sourness. Sodas contain different acids also, again, for taste. And so I know you're familiar with those. Now bases, we don't eat as many bases, but they are, I mean, you have. And foods contain different bases. They are always going to end in a hydroxide as far as the name goes. So dark chocolate sometimes will have that bitter taste. I'm not a fan of dark chocolate. I know some people are, but the unsweetened dark chocolate, you can really taste the bitterness. Raw almonds, if you like those, again, depending on the ripeness, you can sometimes get that pretty bitter taste. And then herbs are used for seasoning and for flavor, and so sometimes that bitter taste is what people are kind of after. Now, reaction-wise, chemically, acids do have one very specific reaction that is that we'll talk about, and those are the reaction that acids will have with metals. And anytime an acid reacts with a metal, it produces a hydrogen gas, and this is a single replacement reaction. And so the metal and the hydrogen basically switch places. And so you have this hydrogen gas that is produced. And then another one, which you've probably seen, is acids reaction with litmus paper. Acids will turn blue litmus paper red. And notice that I have the word red in kind of quotes up there. It's kind of misleading to say red, because if you see that picture over there, the one on the left, it's more of a pink color, so just kind of be aware of that. And then with bases, one of their big reactions is that they will react with acids to neutralize the acids, and they produce a salt. Again, it's a chemical salt, so not necessarily like the salt on your kitchen table, and water. And that's a double replacement reaction, so you have two things trading places and two new compounds formed. And then with the litmus paper, bases will react with litmus paper to turn, again, kind of in quotes, that red litmus paper blue. And so that's the picture over there on the right. And so litmus paper is one of the fastest, easiest ways to test for acid or base. It used to be taste, which they don't really like anymore because, you know, people died from that. So that's why we've came up with things like litmus paper. Okay, so now we need to talk about water again for a little bit. I know we talked about it quite a bit in the last chapter. Water is still a big stinking deal. And so one of the things to know about water is that it ionizes. Not only does it help to ionize other compounds, break them down into a positive ion and a negative ion, water can also ionize itself. And when it does this, and that's this reaction right here, water will break itself apart and reform into a hydronium ion. So that's this H3O plus, and hydroxide. You should be a little bit familiar with hydroxide because it's one of the polyatomics that we did when we talked about naming. But water lives in this dynamic equilibrium. It is constantly ionizing itself and then reforming into water molecules, and then ionizing itself and reforming into molecules. So if you have a glass of water sitting there in front of you, you've got some H2O in there, but you've also got H3O plus and OH minus. And so it's a continuous thing. And this study of water led to kind of the discovery of some things about acids and bases, because they tend to act like water, at least as far as ionization goes. So one of the guys who really studied water, again, I know some of you are like, how in the world could you spend your life studying water? Well, our friend here, Svante Arrhenius, did. And he used this knowledge to come up with a definition of an acid and a base. And so he said that and he called it an Arrhenius acid because he was very humble. He said that any substance that gives up a hydrogen in a water solution and forms a hydronium ion is an acid. And so in this reaction, you have this acid right here. So here's your acid, and it will break into its ions. So you have the negative ion and the positive ion, and almost immediately, because it's in water, this hydrogen will start it all over again, and it will join with a water molecule to form hydronium. So there's our hydronium. So Svante, the handsome guy up there in the corner, spent his life, or some of his life at least, figuring all of this out. And he said, anytime this happens, anytime you see the presence of this hydronium ion, you know that an acid is present. All right, so now he also did some stuff with bases, and he said a base is any substance that gives up an OH in an aqueous or in a water solution. So in this case, here's our base, NaOH, and it will ionize itself basically, and you will end up with this hydroxide. And the presence of this hydroxide tells you that there is a base present. So again, for us, this was not like, I mean, we're not like, wow, that super changed my life. Thanks, Miss Conrad. But it was one of the many reasons that people continued to study chemical reactions and continue to try and figure out what the big deal was, all because of water. So that was really great, but the Arrhenius model is a little bit limited. And the main limitations, first of all, are that it only happens in water solutions. That's true like 99% of the time. Quite honestly, water is involved, but not all the time. So that was a little bit of a limitation. And the fact that he said you always have to have hydronium and hydroxide. Again, that happens like 99% of the time, but not every time. So once Arrhenius got that figured out, two other guys came along and said, good job, Arrhenius, but you may be a little too narrow in your definition. And so these guys, also very handsome, Johannes Bronsted is on the left, and then Thomas Lowry on the right, discovered and kind of redefined acids and bases. So first off, they got rid of the hydronium and the hydroxide thing, and they strictly focused on what they called just a proton, but what we actually know is a hydrogen ion. And they said an acid is any compound that donates a hydrogen ion, but it doesn't have to produce hydronium. So they said as long as there is a hydrogen ion there, we know we have an acid. And a base is any compound that accepts that proton or accepts that hydrogen ion. So no more hydroxide. It's all strictly about what is happening with the hydrogen. They also said that acids and bases don't have to be dissolved in water for this to happen, but that's usually the case. So they just were, you know, a little bit more broad in their definition. And then they said there are some compounds that can act as either acids or bases. It just depends on what the other reactants are. So they will basically kind of do whatever the other thing is not doing. And so again, a pretty broad definition. And this is the Bronsted-Lowry definition is pretty much what we go with now. Okay, so with that in mind, if you are looking at equations with this, it's pretty easy to identify an acid or a base as long as you're kind of keeping track of the H's. So if you look at this first one, in this reaction, HCl is going to act as the acid. And if you look over at the other side, if you look at the products, Notice that you have this Cl over there all by itself. That means that Cl had to have been separated from its H at some point, and that H was donated, or that proton was donated to water in this case, to form H3O+. And so, because it gave up an H, the HCl is acting as an acid. Now, in the other one, we have a base. Now, in this case, the NH3 is going to act as the base. And if you look over at the products, notice that over here I have NH4. That means that it gained an H from somewhere. The only other thing that could have donated the H to it for it to accept was water in this case. And so NH3 accepts the H. That qualifies it as a Bronsted-Lowry base. So if you just watch the H's, that will always tell you what's going on. Okay, so now one other way that acids are sometimes put into categories are based on the number of H's that they have. And so remember that as long as a compound has at least one hydrogen or one proton, then it can act as an acid. And so you have two different classes, of acids. You have monoprotic acids. Remember that the prefix mono means one. So basically a monoprotic acid is anything where you have just one hydrogen. So for example, HCl, the one from the page just before. There's one H there. That one H can be donated, and so that is a monoprotic acid. Now there are some acids that actually have multiple H's, and if it can donate each of those H's, then it is a polyprotic acid. And so in this case, we start out with H3PO4. That is phosphoric acid. That's the one that's in like your Coke. It has 3 H's, and if it donates one of them, gives one of them up to this water that's here, it ends up with H2PO4 and then our hydronium over here. So now I have 2 H's still left. It means it can still give those up, and so it can give up another H to form another hydronium, and now we have this HPO4. One H left, still can donate that one, which it does. So now we're just down to PO4, which is our phosphate polyatomic and hydronium. So this one, sometimes they will call that a polyprotic acid, which is the most common. They could even call it a triprotic because tri is 3 protons or 3 H's. And so it will continuously donate until all of its H's are given away. Okay, and then the last thing as far as kind of naming or defining or identifying acids, you have conjugates. As if just figuring out the normal ones aren't enough, we've got some conjugates. So when an acid donates its hydrogens, the leftover, the remaining ion, which is always negative, could then actually accept a hydrogen because positive and negative would be attracted to each other. And so you actually have the formation of a base after the acid has donated. And that base that is formed is called the conjugate. Okay, so it's the relative base. And it's kind of the leftover. And same thing with a base. When a base accepts that proton or accepts the hydrogen, then it basically becomes an acid. It now has a hydrogen that it could donate. And so it becomes the relative or the conjugate acid that is produced in kind of the second reaction. So in our reaction here, I have 2 water molecules together. Water is super unique in that it can act as an acid or a base, which we've already seen in some of our equations. So it has an H to donate, but it also can accept. It will do whatever it needs to do. So I labeled them. So this red, we're going to say is our acid, the red water, and it's going to give an H to the blue water in this case, which is going to be our base. All right, so now we've got our acid and our base. And then on the other side, we have kind of the leftovers, what remains. And so first off, this acid that we started with, the red H2O, when it gives up an H, it ends up as this OH. So it now has lost an H, so it just has an OH, and it then would be labeled as, I'm going to see, the best way to label this would be, I'm going to put a capital or a C for conjugate. Now it would be considered the conjugate base. Okay, and then on the other the other product, I have my blue water, my base, accepting a hydrogen, and it becomes this H3O plus, and it is now the conjugate acid because it has a hydrogen that it could donate. Now the relatives, or the two that go together, the acid will always go with the conjugate base. Those two are the relatives. And then the base will always be related or will become the conjugate acid. Again, to us, this seems kind of nitpicky and kind of silly, and what's the big deal with this? Chemically, it is a huge reaction, not so much in itself, but knowing what happens, because that gives you a way to predict what will happen in other equations. That will give you a way to predict other products. And so it is, again, kind of a precursor to things that are a big deal to us. So anyway, that's the first part of chapter 21. Let me know if you have questions. I hope you guys are doing well.